All right, we're going to dive into a puzzle, a really old one, like 1,200 years old, that all starts with this crazy simple question. What happens when a math problem has two right answers? It's a question that stumped ancient thinkers. But here's the wild part. The answer they found is actually the secret sauce behind the artificial intelligence we use every single day.
So let's get right into it. This problem comes straight out of a 9th century text. And back then, they wouldn't have written it like this. They'd say something like, squares and numbers are equal to roots, which for us just translates to x squared plus 21 equals 10x. Yeah, it looks like a pretty standard algebra problem, right? But believe me, for the folks who first saw this, it was hiding something huge.
And that secret? Well, it was a total game changer. I mean, think about it. Up to this point, a math problem had one answer. That was the whole point, right? You do the work, you get the answer. But this thing? Nope. This thing completely broke the rules. It hinted that maybe, just maybe, there was more than one way to be right.
Yeah, you heard that right. Two. This one little equation has two totally different, but both 100% correct solutions. And I can't overstate how massive this was. Realizing a single problem could have two answers, that wasn't just a small step, it was a giant leap. It fundamentally changed how we think about numbers and even reality itself.
So the big question is, how did they figure this out? Well, it wasn't with some clunky formula we have to memorize. They used this just really elegant and clever trick called completing the square. And we're going to walk through it because this method, it's the key that unlocks this entire story. Okay, so here's how they did it. It's a really neat process. You look at the number sitting next to the x. In this case, it's 10. Step 1, you just cut it in half. So 10 divided by 2 gives us 5. Easy enough. Step 2, you square that number. So 5 times 5 is 25. Got it? Now for step 3, you take that 25 and subtract the other number from our equation, the 21. That leaves us with 4. Step 4, take the square root of 4, which is 2. And here comes the magic part, the final step. You take that 5 from the beginning, and you both add and subtract this 2.
And just like that, we get two answers. See? 5 minus 2 gives you 3, and 5 plus 2 gives you 7. And the coolest part is, if you take either of those numbers, 3 or 7, and plug them back into our original equation, they both work perfectly. This was mind-blowing at the time, the first instance of two correct answers just popping out of a single problem.
All right, so that's the first puzzle piece. But hold on, because the story is about to get even weirder. Once mathematicians wrapped their heads around the idea that two solutions were possible, their own method led them somewhere, well, somewhere totally unexpected, and frankly, a little controversial. So let's try another one. This time, the old phrasing was, roots and numbers are equal to squares. The scholars at the time thought, okay, no problem, we've got this. They used the exact same completing the square method, followed all the steps they knew worked, but the answer it spat out was something else entirely.
So they followed the process, and sure enough, two solutions popped out. One of them was totally fine, the number 4, no big deal. But the other one was -1, a negative number. And you have to put yourself in their shoes. What does that even mean? How can you have -1 of something? It just didn't make sense in the real world.
And what's so cool about the original texts is how casual it is. There's no big dramatic reveal, no fanfare. Just this simple little note, now negative solution appears. It's so understated, but it's basically recording a quiet revolution. This is the moment these weird, abstract, seemingly impossible numbers elbowed their way into the world of math.
You can just imagine the headaches this caused. It's the exact question that must have kept them up at night. I mean, their entire world of math was built on concrete things, counting sheep, measuring land. What in the world could a negative answer possibly be? It was as much a philosophical crisis as it was a math problem. And the answer, funny enough, wasn't found in more numbers. It was found in a picture.
So here's the big aha moment. The key to making sense of all this weirdness, the two answers, the negative answers, was to stop thinking about it and start looking at it. The second you turn this algebra into a picture, into geometry, everything just clicks. And it's all thanks to this one beautiful, elegant shape, the parabola.
See, every single one of these quadratic equations, when you graph it, draws a parabola, that U shape. And the most important thing about a parabola is that it has this perfect, elegant symmetry. One side is a perfect mirror image of the other, right down a central line. And that one single idea, symmetry, that's the geometric reason for everything we've been seeing.
This is where it all comes together. Remember our two solutions, like 3 and 7? Well, look, that's just the two places where the parabola crosses the main horizontal line, the axis. So what if you only get one solution? That just means the parabola swoops down and just barely kisses the line at its very bottom point. And those times when the math seemed impossible, all that means is the parabola is floating completely above the line, never touching it at all. See, the picture makes it all make perfect sense.
Okay, so this is a really cool history lesson, right? But here's where we pivot, because this is why it matters so much today. This ancient quest didn't just end with a nice drawing. It led straight to the mathematics that powers pretty much everything in our modern world. And I mean especially artificial intelligence.
So, as people got more and more comfortable with this completing the square trick, they started to notice something. The steps were always the same. So they started to generalize it, turning the process into a kind of early proto-formula. You can literally see the original steps baked right into this thing.
And then, over centuries, that early version got tweaked and rearranged into the modern quadratic formula. Yep, the one we all had to memorize in school. It looks way more complicated, for sure, but its DNA, its heart and soul, comes directly from that simple, elegant process the ancients used.
So here it is, the big AI connection. When you're building an AI, your main goal is to make it make fewer and fewer mistakes, to minimize the error. The way they measure that error is with something called the loss function. And guess what that loss function usually looks like when you graph it? Yep, a parabola. So training an AI is really just a fancy way of saying find the exact bottom of that U-shape, the point of lowest error. And the math it uses to do that? It's a direct descendant of that 1,200-year-old trick. It is the absolute core of how modern AI learns.
When you boil it all down, the deepest, most beautiful idea to come out of all of this is just this. Every single one of these equations, every single parabola, is nothing more than a simple, perfect square that's been slid around. That's it. That's the big secret. And from that one simple truth, you get everything. The symmetry, the solutions, and that all-important lowest point. The very thing our most advanced AIs spend all their time looking for.
So, it all leaves us with this one last thought. It started with a simple puzzle about a problem having two answers. And from that one little curiosity, we got a whole new kind of number, a new way to connect algebra and geometry, and eventually, the foundation for artificial intelligence. It really makes you wonder, doesn't it? What other simple, elegant truths are out there, hiding in plain sight, just waiting for someone to ask the right question?